So now for the second short session, probably it will be only 2 seconds today due to our introduction. We may not get through all the exercises, so there may be some left for you, but as I said, we will upload the material. Now, this is about truth tables in general, and in I, the question is this. The number of elementary propositions you find in a compound proposition is called n, and then depending on this, how many rows does the truth table of the compound proposition contain? Okay, that's relatively easy. So I call it, I don't call it anything, but the answer is relatively obvious. Does somebody have an idea?
I think it's 2 power n.
2 power n is correct, 2 to the n, because 2, I put a text here, 2 possible truth values per constituent, okay, per constituent is now this is the same as elementary proposition, or I could also say per input variable. Exactly speaking, or testing this is fine. We had the case with only one input. This is sometimes also called a one-fold compound. So it's not a compound in the broader sense. You know what I mean is, if I take not A, the only input is A, and this is an operation. But since all operations are called compounds in the sense that A and B is a compound expression, so this is also called a compound. But it's, if this is a pairwise compound, or let's say a twofold compound, actually it's a simple compound, but then this one is a one-fold compound. However, this is a case that we have, and we know that the truth table of the not operation contains only 2 rows, and we know why, because A can take on the values 0 or 1. I think I'm getting a little more fluent in English from time to time, because it's been a long time for me to hold a lecture in English, so now I'm a little bit exercising again. Anyway, if we have 2, then it's 4 rows. If we have 3, it's 8 rows. So it doubles every time. This is actually really exponential growth for the number of rows. That makes truth tables actually quite hard to handle if you get if you have more than 4 constituents, then it gets a little cumbersome, yes. But anyway, sometimes it's the best possibility. So now I have, for the second case, I'm curious if you can already tell me.
I didn't understand the second question.
Yeah, and I didn't quite understand, but I would like to explain this first, yeah? So how many pairwise non-equivalent compound propositions can be constructed from n elementary propositions? So this is sort of continuation of part I, because now if we have such a truth table with this number of rows, 2 to the n, the question is, what do we do to construct a new compound proposition without giving it a name? And this is what I do in an example, so to a little bit to lead you to the answer. Or do you want to ask your question now? I thought it was a question, but I didn't understand it.
No, it was just that I didn't understand the second question.
Okay, so is it better now? Did you understand now? You will understand. Okay, I explain on this example. The test example will be n equals 3. So we have 3 inputs. Let's say we have 3 elementary propositions as constituents, P, Q, R, and we know that the truth table now has 8 rows. That's perhaps a good idea to fill them in right now. I use my usual order, you know, that I take ascending binary inputs, and that means that P jumps to 1 now, and then this repeats behind here, 0, 0. Then I have 1, 0, 1, 1, 1, 0, and 1, 1, 1. Now that's the 8 rows of our truth table. But the question is how, you know, this symbol, this is just like a placeholder for any kind of compound operation. Clear? It could be anything. We could also say it's called operation with some name using P, Q, R. This is not so relevant. The relevant thing is what happens when we find a new, or when we build a new such compound with this time 3 constituents. And here I gave you the hint. The hint is every time you build it, you construct an output, and the output in every row can be 0 or 1. So, and this is what I mean with this notation. Okay, so for example, I could I just succeed this way. In every row, I can decide whether it's false or true. So that means I don't have to write it everywhere, 0 or 1. But this is not a logical expression now, so I don't write 0 or 1 because it would be true. No, I mean one of these, okay? But for just as a silly example, I could say I want that in the 0 row, the result is 1. In the next row, I want it to be 0. Then I take 0, like just what comes into my mind. And if I do this in a random way, I get something unique. But next time I must make a change here or there. And then I find out that in every row I have 2 possibilities, and then they multiply up. So it's like I have 2 choices here, 2 here. It means 2 by 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 2. And that's, in the end, the number of factors is 8, and it's 2 to the 8. And this might help you to find the answer to the second question. Because here, say, 8 rows. Some say rows, I say rows. I think both is possible. 8 rows. We said 2 to the 8 non-equivalent compounds. So now the setting is clear, I think. And the question is, how do I get to 2 to the 8? Okay, it's just 2 to the number of rows. The expression would be, in general, 2 to the what? Somebody?
2 power n.
That's right. 2 power n. And then I ask you, should I use some parentheses here? It looks nice.
The 2 power n.
It's actually, it's necessary to put parentheses because otherwise one could think that it's 2 to the power of 2 that quantity to the power of n. And of course it's not, because 4 to the n is something very different from 2 to the n, because this one is actually super exponential. This is called super exponential. It grows even faster than regular exponential function, while this one is simply exponential with the changed base, but still there's a big difference between these two expressions, of course, as you may know. So it's important, and we can't even simplify it. I would like to use the fifth law of potency, but I can't, because if this were a simple product of two exponents, I could put it in a different form, as you may know, or similar. But that's it. That's the easiest way to describe it. I say see example below. So in the example, you could say we tested it. I put it here. 2 to the 3. Okay, 2 power 3. And of course, this is the 8, and so it's 2 to the 8, and it's, what is it, by the way? What's the result then?
256.
That's right. And this is one very famous binary number, you could say, because it's the size of 1 byte, as you may know, right? So that's the number of, for example, of characters that can be coded byte-wise. Obviously, because with 8 bits, which means 1 byte, you have 2 to the 8 possible numbers to encode, which are from 0 to 255, to now information theoretically speaking. But anyway, it's a nice result. Okay, let's proceed, if that's clear. So now it's about logical proofs. It's not so very different from the topic tautologies, because also here we have an equivalence, an implication, and then such a combination. These could, in theory, these could all be tautologies. Actually, it's sort of, if they are valid, they must be tautologies. But this is not our focus here. We want to really prove. And I must say, I think the first is really fast to do, because I remember, is this the same as in the tautology exercise? In fact, no, that's a little different, right? Because we have this and inside. So this one is even simpler, but anyway, we can simplify it further and say this means that the double knot again cancels itself. So we have P equivalent P, and we had seen that now, I don't know, if this is obvious, we can say, fine, that's the proof. It's not really worth doing more than this now in this case, but let's focus to the more interesting cases. The second is, I think it's the best way is the truth table again. But let's look at it first. So it says, see the parentheses, okay? It says, if P implies Q and Q implies R, it follows that P implies R. So if you look at this, you could even give it a name. And it's a well-known formula, a well-known rule, you could say. And actually, it's a special feature of the implication, and it is used in rule-based systems very often. It just says that the logical implication is transitive. Okay, this means it's transitive in the usual sense. So I explain a little what is meant here. Just a moment. Okay. Yeah, you see, it's a chain. It's a chain of implications. If I have an input P, and then I conclude, I imply to Q, then I take Q as another input, and if Q implies R, so you could say the implication is transferred from P to R. So then I have P implies R. It's like a chain of conclusions that I draw. So it's logically absolutely almost clear, but at least it makes sense. Okay, but then to really make sure that it's correct, let's look at the truth table for now. It's the same input as before, but oh, is that right? Yeah. So I just completed, and you help me with the other expressions. You must take every combination into account. That's important. 1, 0, 0, 1, 0, 1. You just start thinking about the others. So now I want to evaluate. I want to evaluate P implies Q, Q implies R. Then I take the AND between these two. This is short notation. And then I even check the value, the truth values of P implies R. And then we look at the final implication, because that's what it, here, you see, I marked it in blue color. That's the essence of this whole formula. Now, help me so that it gets perhaps a little faster. I filled in the first row, I explained. This is the positive case of the implication. This is what we all know. No, it's the negative case. It's the case that this is the premise. Look here. Huh? Premise is false and conclusion is also false, but as we know, this keeps the implication valid. So it's true, right? And the same holds between Q and R. Everything is 0 here. So we have a sort of a passive implication that's always true. This one, and even this one. So now, but the important is this one. We must make sure that both implications are true. That's why we have an AND between them. And 1, 1 is the row where the AND compound is true. And that means, now it means, these two rows must fulfill another implication. And since any implication is true, if premise and conclusion are true, it says true. That sounds more complicated than it is, but that's the way to make it. So help me as fast as possible. P implies Q, true or false? In this row?
True.
Yeah, okay, it's true. I don't know, you probably don't have earphones, and that's why we get a little acoustic feedback, but it's not so serious. Okay, this one, true, false? Now something's different here. The premise fails, the conclusion succeeds. Yeah, I didn't get it.
Well. I can't.
Sorry, yeah, it's hard to hear now due to the echo, but it's fine. It's still true, no? Because as we know, the conclusion can get true without the premise being true. There's no strong coupling between these two. It's sort of a weak coupling, you could say, yeah, of a special sort. Now, P to R, also true, right? 0, 1. We just have to spot the contradiction case where we have premise true and conclusion false. That's the critical case. So we should spot them. But now, the AND is still true, and everything is yet. Now I must take these two columns. Premise true. The whole AND compound is the premise. Okay, in this blue implication. So that's why I say premise true and conclusion true, and so everything's true. And it goes on, but we must take care. Okay, P to Q. You'd help me if I make a mistake. 0, 1, 1. I look at the implication. QR. So now here, perhaps I should make a mark here. Now I see that This is the contradiction case, because the premise is true, the conclusion is false. That means I must definitely put a 0 here. But now, again, R is 0. Oh, no, sorry. A P and R, we look at P and R, 0, 0 gets 1 again. So now we almost seem to get a problem here. Now, not really. Now, because this time, since 1, 0, I have 1, 0, this time the AND fails, the AND gets false. But this is not serious because a 0 still implies 1, as it means now for this blue implication, blue, please look back here. That's what I mean with blue. Now, in this case, I leave it visible. We have no problem, and the total implication stays true. So now it's almost clear what we're doing. P to Q seems 1. Q to I just say Q to R. I mean Q implies R. Okay, is the positive case this time, so it's true. 0, 1 for P and R is also fine. So now we have everything with ones again. Please look. Keep looking, because if I speed up, we could make mistake. Now here, 1, 0, that's a contradiction case again. So here I see another 0. But Q implies R is fine. P implies R that's now interesting. We have another fail. So even P implies R is wrong. And before we think, oh, now it's done. It does not work. What's the point? What do I do? We have two contradictions in the sense of implications. So neither P implies Q nor P implies R, which is the conclusion of our whole statement. The conclusion is false, but the premise, this is missing. What is it? Remember, it's the AND compound of these two implications. And since they are not both true, this one is false. Yeah, and that's the reason why this goes fine. So because 0, 0 is premise 0, conclusion 0, so the implication stays valid. It's true. Okay, so that's the way you do it. Okay, then again, but this time it's only one contradiction, and the others are fine, I think. Yeah, but this time, oh, sorry, the AND is false again, but P implies R in this case is true. There's no problem. It's again 0 implies 1. In that sense, it's wrong premise, true conclusion. That means it's true in the end. So 1. Help me. Q implies R. Yes or no? In this round?
It is 0.
Yeah, this is my next, I call it contradiction, but of course it just contradicts one of these implications, and so that gets false. And is 0 because they are different, and P implies R that's the mirror case of the other one. So we have a second fail here, but still the main implication stays true or gets true. Premise and conclusion are false. So in the last round, this is perhaps the the active case where all these implications take place actively because everything is true, every constituent is true. So I think that's no question that we get ones here. So in the end, this was the proof because the whole column is true. In any case, this holds. It means it's a general rule of chained implications called transitional law or law of transition. Well, it's sorry, I wanted to say transitivity. Okay, the third, it's nice, but I must save a little bit time, and the time is all over almost. So 2 exercises are remaining. No problem. I will show them in short. You can make screenshots and then really try to solve them by yourself. Perhaps we can make a short discussion then next time. So now I make a proposal. This is also interesting because it means we have 2 implications. P implies R and also Q implies R. So you remember that the premise is sufficient for the conclusion. That means here P is sufficient for R, but Q is also sufficient for R. And since this is and compounded, so and combined, it means that both is true. Yeah? P and Q are sufficient for R, but they are sufficient alone. That means if P is sufficient and Q are sufficient, I don't need them both to be true. One is sufficient. So one is enough, yeah, to be true. And then if we look here, this is an or, and that means we see here that the or compound is true even if only P or only Q are true. If they're both false, then it gets false, only then. But if they're both false, also here both premises get false, and then we might, but we won't have a problem immediately because in the end this will be well, then you must look what results. But the interesting conclusion here is that the whole thing implies R. And I wanted to argue that since this rule says that P is sufficient for R and this says Q is sufficient for R, and since we know, or we suppose, that either P or Q are true, it means one of these sufficiencies takes place and so R gets true. This was only the positive case, okay? So this is not really a complete proof, but it's very reasonable to believe that this is always correct. We can test the negative case also, that would almost be enough. Because if R is false, it means that, now think back to the contradiction case. If the conclusion gets false, then all possible premises must also be false, because each one of these, if it were true, would suddenly make R true, if all of this is correct. So if R is false, I can backward conclude that Q and P must both be false. And so this and is already false. Neither this nor this would be true. And since Q and P are both false, the OR will also be false. So in the end, this and this is 0 and 0 and 0. This is totally false. So I have false if R is false, and I have a clearly true on this left side. The premise is true. In total, it's true if R is true. And that's why we can be sure that it's correct. But this is, of course, this is a very, very shortened proof, I admit. And the time is over. And, unfortunately, okay, just stopping now.